biconvex lens is formed from two lenses. From the setup, we can see that both of these are in contact. The radius of curvature R for both the surfaces is 14 centimeters. So we are also given that data and the refractive indices of both the separate lenses. For an object at a distance of 40 centimeters, find the mesh distance. Now we can treat this as refraction at two spherical surfaces, or there could be another approach. What do you suggest, Jay?
See, this can be solved by the method of refraction at two surfaces, but that is long and lengthier. So the best approach will be to take this biconvex lens as a combination of two lenses which are in contact. So basically, we will have two lenses where each lens will have one planar surface. So if we do it like that, we'll just have a simple we just have a formula. We just need to apply that, and the question will be ready and solved. So what does that formula say? The formula say that let's that the very basic lens maker formula says that 1 by b minus 1 by u is equals to 1 by f. So here the f of combination will be the f of the individual f of the sum of the individual reciprocal of focal lengths of each lens. So it will be 1 by f1 plus 1 by f2. Now we use the lens maker formula for f1 and f2. Now so the 1 by v minus 1 by u will be equals to n1 minus 1 by 1 by r1 minus 1 by r2 plus n2 minus 1 by 1 by r2 minus 1 by r1 dash. So here basically r2 is the radius of curvature of this planar surface, which is common for both. So I have written r2 and r2, and this the r1 is this and r1 dash is this curvature of this. So by considering the Cartesian sign of convention, we get 1 by v is equals to 1 by 1 minus 40. See, the u is minus 40 plus 1.5 minus 1 1 by r1. So the r1 will be positive because it is in the we are considering the direction of incidence ray like this. So r1 will be taken as positive. And since this is a planar surface has a radius of curvature infinity. So this will be 1 by infinity plus 1 by 2 minus 1, and this will be also into 1 by infinity minus 1 by minus 14. See, in this case the radius of curvature, the center of curvature is at the opposite direction of the direction of the incidence light. So the radius of curvature is negative. Now from this, just we need to solve this, and we will get v is equals to plus 40 centimeter. So plus 40 denotes that v is found at here.
Okay, to summarize, we simply considered this problem to be the problem of two lenses in contact, and then we applied the lens maker formula as well as the simple lens formula and got the answer, which is 40 centimeters. Look at the question. The setup is given in which a concave or convex lens with its convex face silvered is there. So this acts like a concave or convex lens in contact with a concave mirror. Now we have the radii of both the surfaces given, and we need to find first the effective focal length, and then when the concave part is filled with water, whose refractive index is given, we have to again find the focal length. Jaya will give the solution.
See, in this question, the setup can be since the setup has in this setup one face of the lens is silvered, we could basically consider a silvered lens as a combination of a lens and a mirror uh, in contact. So, um, so basically, in this, the effective focal length will become two times the focal length of the lens minus one time the focal length of mirror. Big, uh,
Can you explain how you got this formula?
See, in this, the in this, when the light comes from here and travels inside the lens and it goes out. So in this, what basically happens, the light traveled two times the lens. So that's why we get two times the 1 by focal length of lens. So it's basically like placing the same concave lens two times, and the focal length of the mirror is subtracted because it's changing the direction, and the focal length of this mirror is in the opposite direction of the incident light. Now, since the formula is known, we will just simply use the lens maker formula to calculate the focal length of the lens, and then we will apply this formula to calculate the effective focal length of the combination. Now, for the f of lens, focal length of lens, the f of lens will be equals to 1.5, let's say mu minus 1 by 1 minus r1 minus 1 by r2, which will be equals to 1.5 minus 1 by 20 minus 1 by 60. So 1 by f effective. So 1 by f effective will be equals to 2 times of 1.5 minus 1 into 1 by 20 minus 1 by 60 minus 1 by the focal length of the mirror, which is minus 10. So in this case, we will get f effective as minus 7.5 centimeter. So the A part is done. Now we will proceed to the B part. In the B part, the water is filled. So basically, when the water is filled, when the water is filled, it can be considered as a separate lens. Like this, when the water is filled, the liquid water can be considered as a separate lens in front on the given lens. So it will be basically broken into this: a planar lens, a convex or concave lens,
Concave or convex.
sorry, and a mirror. This is the liquid. So in this case, 1 by f effective will be equals to 2 times the f of the liquid, which is water, plus 2 times the f of focal length of lens minus 1 by focal length of the mirror. So this is pretty straightforward as we have done the part A, and extra term of twice the reciprocal of focal length of what of the lens formed by the water is added. So basically 1 by f effective will now be equal to twice of 4 by 3 minus 1 into 1 by infinity, because this is a flat surface, y is equals to infinity, minus 1 by minus 60, as curvature of this is equal to the curvature of this, plus 2 times 1.5 minus 1 to 1 by 20 minus 1 by 60 minus 4 1 by minus 10, which gives focal length effective as minus 90 by 30 centimeter.
So in this problem, we simply broke it down again into a combination of lenses and mirrors, and in the first case we made it a combination of two concave or convex lens placed and a concave mirror placed between them. And in the second case, we also added the lens formed by the liquid, and then we applied the lens maker formula also to finally get the answer. The angular magnification of an astronomical telescope is 36, and diameter of objective lens is 75 mm. So that means we know m theta, for which we have a formula, and also we are given some data, one of the variables, that is the diameter of objective lens. We need to find minimum diameter of the eyepiece to collect all the light entering the objective lens from a distance point source. Jai will give the solution.
So basically this question involved a straightforward formula from the astronomical telescope optical instrument. So in astronomical telescope, the angular magnification m of theta is given by negative of focal length of objective by the focal length of the eyepiece, which will be equals to and can be extended to the diameter of objective by the diameter of the eyepiece. So basically we should remember that diameter is not the radius of curvature, it's basically the aperture. It's this. This is the diameter d. So from the question, 36 should be equals to the diameter of objective, which is 75 by the diameter of eyepiece. So this will give me the diameter of eyepiece as approximately 2.08 mm.
This question is about optical instruments. Object is 10 mm from the objective lens of a compound microscope. The lenses are 300 mm apart, and the intermediate image is 50 mm from the eyepiece. So we are given a basic data setup. We have the basic data about where the lenses are and where the object is. Find overall magnification.
So this question involves some formula from the compound microscope and some basic idea of how the object are placed in a compound microscope. So from the question, we could directly figure out the focal length of the objective lens and the focal length of the eyepiece.
Okay, so can you tell us how this is?
See, in a compound microscope, there are two lenses. This one is objective. This one is eyepiece. So in a compound microscope, the object or the slide which we are viewing is always kept nearer to the objective lens and is at the focus of the objective lens. So this is suppose f of focus of focus 1 of this is for focus of the objective, and this is the object. So as in the question it is given that the object is 10 mm from the objective lens, so we could directly conclude that the f of objective is equals to 10 mm. Now as the image is kept at the focus of the objective lens, the image the image formed after striking the lens will be parallel to the principal axis. So after since these rays are parallel, so this parallel rays after striking the eyepiece lens will form an intermediate image which will be obviously at the focus of the eyepiece. So this will form an image somewhat here which will be also inverted. Now this is the focal length of the objective. This is the focal length of the eyepiece. Now since in the question the distance of the intermediate image is given from the eyepiece, so we could directly conclude that the focal length of the eyepiece is 50 mm. Now we know that f f1 f2 is there, that is the another focal length or focus point of the objective lens, and this is f of objective, and this is s, which is used in the overall magnification of the lens. Now from the question from this question and this setup we have drawn, we get s equals to the the length of the telescope, which is 300, minus the f of objective minus the f of eyepiece, so which is minus 50 minus 10 mm, which gives us s as 240 mm. So the angular magnification can be directly calculated by the formula as we have discussed earlier in the theoretical part, is s by objective into d by eyepiece, where d is equals to 25 centimeter, which is the near point. This implies m is equals to minus